We were discussing about register loaded amplifier before we went to lunch. In the amplifier, when you discuss about amplifier, GM is equal to the change in ID with respect to change in VGS. That is by definition. GM, you know the definition. By definition, GM is equal to change in ID by change in ID with respect to change in VGS. If you put it in analytical form, take the differentiation of ID with VGS, the expression that we get for GM is 2ID divided by VGS minus VT. Now AM or A, the amplification or gain is equal to GM into RL. That is the amplification. So now we know the expression for GM, multiply RL with that. So the numerator now becomes 2ID into RL. Denominator is VGS minus VT. Now ID into RL is equal to VRL or voltage across the RL. That is VRL. So A is equal to 2 times VRL by VGS minus VT. Now A will be maximum when VGS minus VT is minimum or VRL is maximum. The maximum value of VRL is VDD. Therefore, A max is equal to 2 times VDD divided by VGS minus VT. Now, in all these three expressions, the denominator VGS minus VT that actually indicates in terms of bandwidth that if we have VGS minus VT, we will get higher bandwidth. The higher the VGS minus VT, the higher is the bandwidth. This we have already discussed. When we started discussing about bandwidth, we said that bandwidth is proportional to VGS minus VT. This we have discussed. So VGS minus VT will increase the bandwidth, but VGS minus VT, if you look at this, A is inversely proportional to VGS minus VT. So VGS minus VT, if we increase, A will decrease, which means the gain will decrease. It will reduce the gain. So while we are trying to increase bandwidth, we are reducing the gain. But gain again we have seen is dependent on VDD. So low VDD will again limit the gain. So if we have lower VDD, VGS, we are trying to increase the bandwidth, then gain will be very limited. So this puts limitations on the gain in the register loaded amplifier. If you consider a register loaded amplifier, the limitations on gain is due to VDD. Low VDD gives lower gain. Higher bandwidth require VGS minus VT to be higher. That also reduces the gain. So these are the two factors which affect the gain. Now, how we are going to implement the register loaded amplifier? So this is a typical circuit diagram of implementing register loaded amplifier. Here you can see the two resistors which are loaded with the amplifier are R1 and R2. Those two are loaded here, and you can see the total amplifier circuit here. How many amplifiers we are using, how many transistors we are using, you can calculate 1, 2, 3, 4, 5, 6, 7. 7 transistors are used. These are in cascaded. We have 2 fixed. So this is a typical differential pair using. So you can see 2 differential pairs. In the top, M1 and M2 are differential pair. M3 and M4 are differential pair. So we have 2 differential pair amplifiers in the top, and this is basically a typical implementation of differential pair. Basic benefit is bias stability without feedback. You don't require a feedback here. From the output to the input, feedback is not required. Bias is stabilized. We get a stabilized bias, and we have a good common mode rejection ratio. CMMR, common mode rejection, CMRR, common mode rejection ratio is good. When we say this common mode rejection ratio and slew rate that I told you earlier, these are all terms that you will maybe you will be reading later when you read operational amplifier. These terms are actually related to operational amplifier. Operational amplifier is realized using differential pairs. So once you have a differential pair of amplifier, that is going to give you something called common mode rejection ratio. So don't worry about it. Just remember that it has a good common mode rejection ratio. When you use resistor loaded amplifier, it has a good common mode rejection ratio. Now, what are the negativity? Negativity or the drawbacks? It requires more power than a single-ended version. So if you use one amplifier or one device, that will require, definitely that will require less power, because two devices, both of them are consuming power, both of them will consume same amount of power. Therefore, if you use more than one device, the power input will be increasing. So more power is required than single-ended device. Then we will come to the open circuit time constants that are associated with these amplifiers. The time constants, open circuit time constant, that we are going to discuss. The Miller capacitance analysis actually is a reasonably good method to know this, the open circuit time constant, because you know the time constant. How do you find out time constant? For time constant, you find out by 1 by T. T is equal to 1 by RC, 1 by LC. That way you find out. So always 1 by RC. C is the capacitance. So that you should have some knowledge of the capacitance. That knowledge comes from the Miller's circuit. So the Miller capacitance analysis is a reasonably good method to find out open circuit time constant. But problem is it is somewhat limited in applicable topologies. In all topologies means all types of circuits that you design. The design or the arrangement of circuit, that is the topology. In all types of topologies, this is not applicable. This may be limited there. The OCT is open circuit time constant. So the OCT method is more general and often gives more insight. This is systematic, intuitive method to determine bandwidth of the amplifier. Once you know the time constant, as you know, T, capital T is equal to 1 by F, or F is equal to 1 by T. So frequency and time are related. So therefore, if you know on the time constant, you can estimate the bandwidth. So there is a dominant pole, often gives fairly accurate estimate of the bandwidth if there is a dominant pole. Points to bandwidth bottleneck. These are the bottlenecks for bandwidth is, this is the real value of the OCT method. So you can find out what are the bottlenecks of bandwidth from the OCT method, using the OCT method. We are going to discuss OCT method in some details later. Limitations, it fails in RF circuits with zero enhancement or inductors. So if you have inductors and the time constant is not 1 by RC, so you cannot find out the time constant, so it fails there. Similarly, with zero enhancement, it fails there. In typical broadband amplifier, the OCT will estimate too pessimistic. Estimate due to OCT is too pessimistic. So it is negative estimation typically in broadband. This is because of multiple poles at around similar frequency. Same frequency, you have multiple poles. I hope you understand what is meant by pole. You know, if we take this AV is equal to V out by V in. Now, for this AV, we can express it in terms of a polynomial. When you express any polynomial, then the polynomial can be expressed as the ratio of two other polynomials. So if you have the numerator, when you equate numerator to 0 and solve that, the values, the solutions that you get, those are called the zeros of the polynomial or zeros of AV. Similarly, when you solve the denominator, equate the denominator to 0, solve it, the solutions that you get, those are called the poles. If you get only one solution, then there is only one pole. If you get more than one solution, then there are more than one pole. So there can be more than one pole. At the same frequency, there can be more than one pole. For example, if you consider 1 by x square minus 1. So x square minus, if you consider 1 by x square plus 1 plus 2x. So x square plus 1 plus 2x, so minus 2x. X square minus plus 1 minus 2x. So x square minus 1 plus 2x. X square minus 2x plus 1. That is same as x minus 1 whole square, which means you are repeating the pole. The root is repeated at 1. Similarly, so that is what is meant by due to multiple poles, means same point, same value x has 1 and 1, two values, but both are same, around the same frequency or similar frequency. Now let us consider the method, OCT method. For this, assumptions are no zero near or at WH. So there is no zero WH when W is equal to omega is equal to omega S. There is no zero. So numerator will not go to 0 when omega is equal to omega H. 0 will be well below omega H, and that is handled by treating corresponding capacitor as short circuit. So that is the second assumption. Third assumption is negative real poles only. Only the poles are negative and real. There is no complex poles. So complex conjugate poles with low Q, they reduce the accuracy of the estimation only moderately. There are no inductors. So these are the four assumptions for the OCT method. Now we know what is A. AS is equal to V0 by Vi. AS is the gain or amplification, is equal to V out by V input. So V0 by Vi, that is given as A0 divided by 1 plus tau 1s into 1 plus tau 2s up to 1 plus tau ns. So it means it has n number of poles. So that you can write as A0 divided by, if you multiply all the terms in the denominator, that will be 1 plus tau 1 plus tau 2 up to tau n into s. Then tau 1, tau 2, tau n into s to the power n. So that way it will be the denominator. Now if we ignore the higher order terms in the denominator, by ignoring the higher order terms, omega h is equal to 2 pi h. That will be approximately equal to 1 upon tau 1 plus tau 2 plus up to tau n. Or that you can say 1 upon a series I is equal to 1 to n over the series summation over I of t tau I I equal to 1 to n. So omega h or 2 pi h is approximately 1 upon r tau 1 plus tau 2 up to tau n. Now that we can rewrite as this summation over I of tau. So tau I summation from I is equal to 1 to n. That let us rewrite as summation from j equal to 1 to n tau j0. That also, this way also we can rewrite that. So that we can show. So if we do that, then omega h is equal to is approximately equal to 1 upon summation over j equal to 1 to n tau j0. Now what is tau j0? Tau j0 is equal to rj0 cj. This is the time constant. Open circuit time constant. O is for open circuit. So considering the open circuit time constant is this. So open circuit time constant now can be found out without node equation, without using any equation, just by inspecting. Once you know what is R, what is Cj, you can find out what is the open circuit time constant. Once we know what is the open circuit time constant, we can find out what is omega h. So now let us consider some arbitrary circuit which has resistors. It has dependent sources, voltage dependent sources, current dependent sources, etc. And it has n capacitors, but it has no inductor. Redraw the circuit to pull the capacitors out around the perimeter. So we are looking at the left hand side. So all the capacitors are outside. C1, C2, Cn are outside. Inside is the black box which contains the time dependent sources, resistors. It has only resistors and sources. There is no inductor. On that also you can do in this manner. The left hand side, R10, R20, Rn0. So this is same thing as the left hand side. The right hand side is same. Only thing is we are replacing the capacitance with equivalent reactances. Now consider DOCT for a common source amplifier. We have this common source amplifier here. Then you have the two capacitances connecting the drain to source and drain to gate. Sorry, gate to source and gate to drain. These are there. And the circuit is there. You can see what is CGD, what is CGA, that you know, gate drain, gate source, then R20, R10, R30. These values you can see, find out easily, just inspect it. You can say R10 is equal to Rs. Tau 10 is equal to Rs into Gs. Once you know what is R10, then tau 10 is equal to R10 into CGS. So CGS is tau 10 is equal to Rs into CGS. Similarly, R30 is a RL. Since R30 is equal to RL, therefore tau 30 is equal to RL into CL. Only thing is, to find out R20, you require somewhat is required to find out what is the exact value of R20. But R10, R30, that you can find out easily. R20, for R20 you have two resistors, Rs and RL. Both are there. Therefore, it requires some work to figure out what is R20. Now use the equivalent circuit of the transistor here. We have RL, we have RS. Transistor is the current source, so Gm into VGS. VGS is the voltage between gate source, V0, those things are there. Now find out what is VGS. VGS is equal to IT into RS, that we know. What is VGS? IT into RS. Then minus V0, which is the output. Minus V0 is equal to IT plus GM VGS into RL. That you can write as, if I take IT common, then that is IT into 1 plus GM VGS by IT. VGS by IT is RS. So 1 plus GM into RS into RL. So, and then VT is equal to VGS minus V0. So that is VGS minus V0. That is equal to, you know, expression for VT, V0. We know expression for VGS. So VGS minus V0 will be ITRS plus IT into 1 plus GMRS into RL. Now take IT common. If you take IT common, it is 1 plus RS by RL plus GM into RS whole into RL. Now you can find out what is R20. R20 is equal to VT by IT. Now VT, we know IT is there on the right hand side, divided. So R20 is equal to 1 plus RS by RL plus GMSRS whole into RL. Now you can find out, once we know what is R20, we can find out what is tau 20, time constant. That is CGD into R20. So now we have found out what is R10, what is R20, what is R30, what is tau 10, what is tau 20, and what is tau 30. Now if look at this, if RS is equal to 0, then tau 10 is equal to 0. Similarly, tau 20 now becomes, once you put RS is equal to 0, tau 20 is equal to CG into RL, because other terms will cancel out. And tau 30 is equal to CL into RL. So RL determines the bandwidth here. In all these three cases, since it is multiplied by RL, so RL determines the bandwidth when RS is equal to 0. Having individual OCT values identifies the bandwidth bottlenecks and suggests how to change or how to design it. So those plans you can do. Note that for cascaded amplifiers, CL does not include Miller capacitance of the next stage. So tau 20 corresponding to the next stage Miller capacitance is separately calculated when you consider the uncascaded amplifiers, because CL does not include it. Then we come to the next configuration, which is called the cascode. Cascade we have seen. Now look at the cascode amplifier. Cascoding is a technique by which we improve the bandwidth and we improve the stability. Both are improved. What we do here is you connect the source and drain. So take two transistors, connect their source and drain. So that is what is basically done here. Source and drain are connected, gate remains as it is. So for one transistor you ground the gate, for the other transistor through the gate you will give, between the gate and the ground you will give the input. So this configuration is called cascaded canal configuration. In this AV is equal to, you can see this, the midband gain, and AV is equal to minus GM1 into RL. And now the analysis is shown here. I am not going to explain it, you can easily understand. R10 is equal to RS here, R20 is equal to RS plus 1 plus GM1 RS by GM2 plus GM2. Then R30 is RS effective in parallel with 1 by GM2 effective, which is equal to 1 by GM2 plus GMB2. R40 that is approximately equal to RL. Now these are simple calculations which we can do for cascaded amplifiers. Therefore, cascading improves the bandwidth. In a single stage amplifier, you don't require the cascading. Single stage, you improve the bandwidth. Problem with cascading, cascading is bias point. This reduces omega t of the next stage. PMOS SF is a possibility, but low GM/Y ratio is a drawback. So don't go for PMOS SF. So with that, we come to the end of the discussion for today. We'll discuss in the next class. The rest portion we'll discuss in the next class. If you want the PDF sites, please go to the MIT Open Courseware site that I have given you. Otherwise, I will